Welcome back, just in time for the Law of Cosines. We've already talked about Law of Sines in two other podcasts, part 1 and part 2 of that. But now I'm going to address Law of Cosines, which is another technique we can use for solving an oblique triangle. Given certain information about oblique triangle, we can then find the rest of the information as far as angles and side lengths. Okay, so for the Law of Cosines, I want to first develop the formula so you can see where it comes from, and then write out the formulas and then show you some examples of just how to use them. And then we're going to conclude with another formula for area of a triangle, which actually gets derived from Law of Cosines. I'm not going to go into the derivation of it, but I'm going to show you how to use something called Heron's formula to find the area of an oblique triangle. Okay, so Law of Cosines, where do we start? First, we need to start out with looking at a triangle, because I want to derive the law. So I need to sketch a triangle here. So I'm going to draw, sketch whatever, the XY coordinate system. And then we're going to put vertices on here about in these locations or so. It needs to either be in quadrant 1 or quadrant 2, but drawing it in quadrant 2 will be our best way to really see what's going on here. Put on that third vertex up there. Okay, so we have this triangle here. We're going to call this vertex A. We're going to call this vertex B, and this vertex C. Vertex B on the XY axis system is located at 0, 0. Vertex C we're going to say is located at A, 0. So we're going to let that x value be little a. And then we're going to figure out what vertex A's coordinates are. We don't know yet, but we're going to figure it out. Alright. Now, from vertex A, you can draw a perpendicular here and make a right angle with the x-axis. And then in turn, it makes a little right triangle right here. And we can say, well, this length here is some x value, and this length here is some y value, because you got x-axis versus y-axis. And then we can label this point here capital D. Okay. And then we also have sides, side A, side B, side C. That didn't turn out very well when I wrote side C there, but there we go. Okay, so if we look at this, we can use our knowledge about angles and trig ratios. And we can look at angle B here. And if x and y are the coordinates for vertex A, we can rewrite that a little differently in terms of angles. Because if we look at angle B, whether angle B is obtuse or acute, it's not going to matter. We can say, well, the sine of B, we can look at this right triangle here, or if it was in an acute angle, we could look over here at a right triangle. But the sine of B can be said to be opposite over hypotenuse, so y over c. Then we can go and solve for y and say, well, y equals c times sine b. Alright, and then for cosine of b, we can go ahead and say, well, that's x over c. And we don't have to worry about SIGN signs, because in quadrant 2, x will be negative, which will take care of negative cosine in that quadrant. Or if the triangle were all in quadrant 1 here, it would be positive. X would be positive and the cosine would end up being positive. So either way, whether angle B is acute or obtuse, this is what we can say. And then so therefore x equals c times cosine b. Knowing that, we can rewrite the coordinates for point A. Instead of saying x comma y, we can say c cosine b, c times cosine b, comma, c times sine b. This is going to be very helpful when developing our law of cosines. Okay, so we've got all these coordinates. We've got point C has coordinates a0, point B has coordinates 0, 0, and point A has c cosine b, comma c sine b. All right, now let's find the length of side B. Let's do that using the distance formula. The distance between points C and A can be found by the distance formula, and that in turn will give us the length of side B. So distance formula, we got square root. Then we're going to take the x coordinates, subtract them, so the c times cosine b minus the a, quantity squared, plus, then we'll take the y coordinates, c times sine b minus 0, quantity squared, and then take the square root of that sum. Take both sides, square them. We got b squared equals, and then we got the c times cosine b minus a squared. Squaring both sides, we can get rid of that square root sign, plus c times sine b squared. Okay, so b squared equals, let's see, FOIL out c cosine b minus a, we're going to get c squared times cosine squared b minus 2a c cosine b plus a squared. Then for this plus, we got c squared sine squared b. All right. If we take c squared well, let's rewrite this a little bit. Let's write a squared plus, we got two terms with c squared in them, so we're going to say c squared and then factor out cosine squared b plus sine squared b. And then we still have the minus 2ac cosine b. Then we have b squared equals, well, cosine squared b plus sine squared b actually equals 1. That was one of those identities we learned a while back. Sine squared plus cosine squared equals 1. You could reverse it, cosine squared plus sine squared. So we've really got a squared plus c squared minus 2a times c times cosine b. And this, my friends, is one of the formulas you can use to solve an oblique triangle. This is part of the law of cosines. If you know, this formula directly helps you to solve for a missing side if you know the other two sides and know the angle between them. So like if you know side C and side A and then no angle B between them, you can solve for side B over here. Or if you know all three sides, you can solve for an angle. You can use the formula in a couple different ways. Now a similar proof will show that a squared equals b squared plus c squared minus 2b times c times cosine of a. There's actually three formulas here. Each one solves for a different side. We also have in the law of cosines that c squared equals a squared plus b squared minus 2ab cosine of c. So we've got three formulas we can use now for solving an oblique triangle. So what I want to do is go through and use it, apply it, show you how to use it. We're going to use it for side angle side. We're also going to use it for side side side. And then I'm also going to show you that you can actually use law of cosines to deal with that case in the law of sines that's up in the air, and that you can have the one triangle, zero triangles, or two triangles. With law of cosines, you can quickly do that one without having to worry about doing too much analysis on how many triangles are possible. So we'll talk about that in a minute too. All right, so let's do an example. This example is going to be side angle side. But it's going to be related to using law of cosines to solve here. All right, let's draw a triangle ABC. Sketch, I guess. I'm not really drawing. I'm not using a straight edge, but sketch it. Triangle ABC. Okay. And let's say you know that B is 73.5 degrees. And then you know that side A is 28.2 feet. And you know that side C is 46.7 feet. Oops, down here, not up there. Okay. And you need to solve this triangle. You need to find all the missing pieces of information. You only have one angle so far, so you really can't go in and try to find the other two angles by using the fact they add to 180 yet. So we're going to have to hold off on that. But looking at this, what you can do is you can say, well, I know that side A is that, I know that side C is that, and I know the included angle B is here. So the law of cosines will allow me to solve for side B by saying B squared equals A squared plus C squared minus 2 times A times C times cosine of B. Alright, so solving for B squared, we got B squared equals, we know A is 28.2. We got 28.2 squared plus C is 46.7. 46.7 squared minus 2 times 28.2 times 46.7 times cosine of angle B, which is 73.5 degrees. Okay, so let's put all that into our calculator. 28.2 squared plus 46.7 squared minus 2 times 28.2 times 46.7 times cosine of 73.5 degrees. Enter. And you get that. And then take the square root. Make sure I put everything in correctly. It was 28.2 squared plus 46.7 squared minus 2 times 28.2 times 46.7 times cosine 73.5. And this is in degree mode, right? Yep. Just double checking. Okay, and then that's supposed to be B squared, so then second square root of second answer, enter, and you get that. So B is around 47.2 feet. All right, so now we've solved for all three sides. Now the trickier part that's left is to find the remaining angles, but we can do that with law of cosines. We've got to find angles A and C. Well, side A is 28.2 feet. Well, side C is 46.7 feet. Since side A is shorter, let's go ahead and go through here and try to, let's look at angle A. Angle A is going to be the smaller angle compared to angle C. So angle A cannot be an obtuse angle. It has to be smaller than angle C. And actually, if you look really closely at this, angle B is 73.5 degrees, while side B is 47.2 feet. Side B is the longest side, which means angle B is going to be the biggest angle. So the remaining angles A and C must be acute. So there's not going to be any question about whether we should take an acute angle or versus an obtuse angle because of the way the sides and the angles in a triangle are related. The smallest side is always going to be opposite the smallest angles. The largest side will always be opposite the largest angle. And also, when you look at the angles and add them up, or look at the sides and add them up, the sum of any two sides has to be greater than the length of the remaining side. And all these different relationships with this triangle help us to kind of analyze, well, what should we look at first? But let's go ahead and solve for that smaller angle first. But we know they all have to be acute based on what we already know about angle B. Now, if one of these two was going to be the largest angle, I would say go solve for the smallest one because you know it's going to be acute, and then from there you'll be able to easily find the third one. Alright, so let's do this. Let's use law of sines. We can say that the sine of angle A over side A is going to equal the sine of angle B over side B, because we know side B. And then this will find the smallest angle for us. So sine of A over side A, 28.2 feet, is going to equal the sine of 73.5 degrees over the 47.2 feet. Okay, so sine of 73.5. Whoops, it looks like I tapped that twice. 73.5 times the 28.2, which was provided to us, so we know that's exact. And then divided by the 47.2. I'm going to put a little more in there because that was rounded from the answer I had gotten. Okay. And that's what sine A equals. So then do the inverse sine of that answer, and you get around 34.9 degrees. So we got 34.9 degrees. But you know, then from there, if you know two of the angles, you can subtract from 180, and then you're good as gold. 180 minus the 73.5 plus 34.9 that we just got. Let's see, add those together. And then subtract from 180. So we got 71.6 degrees. And now we have solved that oblique triangle. Alright. Let's solve another one. This one was side angle side. Let's solve one where we know all three sides. Side, side, side. Let's use law of cosines to help us to figure out the angles in such a triangle. Okay, triangle ABC yet again. Side A, the shortest side, is 25.4 centimeters. Side B, the middle side, 42.8 centimeters. Side C, longest side, 59.3 centimeters. And we're going to be solving for angles A, B, and C here. Okay, so we can use the law of cosines to solve for any angle. We'll solve for any of those angles. Let's see here. The angle opposite of the longest side is side C, so angle C is going to be the largest angle. We know that angle C is obtuse if the cosine is negative versus positive. So that's why we're going to start with the biggest angle to figure out, if we're going to have an acute or obtuse angle there. And then once you figure that out, the other two kind of fall into place. So we're going to use c squared equals a squared plus b squared. At first it looks like the Pythagorean theorem, which if you do have a 90-degree angle there, 2ab cosine c. If c is a 90-degree angle, cosine of 90 will be 0. So this whole thing will cancel out, leaving you with c squared equals a squared plus b squared, leaving you with the Pythagorean theorem. But we're dealing with non-right triangles right now, or oblique triangles, so this whole term here is essential in the formula. All right, 59.3 squared equals 25.4 squared plus 42.8 squared minus 2 times 25.4 times 42.8 times cosine of whatever c is. Alright, let's pull up our trusty calculator here to help us with this whole string of calculations. I'm going to go ahead and do 59.3 squared, subtract 25.4 squared, subtract 42.8 squared, and then divide by negative 2 times 25.4 times 42.8. That's how that's going down. So first it's 59.3 squared. Whoops. Then I'm going to subtract 25.4 squared. Then I'm going to subtract 42.8 squared. And then I'm going to divide by negative 2 times 25.4 times 42.8. Okay, so I'm dividing by this part right here, and that's going to equal cosine of c. And it turns out this is negative, which means that the angle would end up being in quadrant 2. So you'd end up with an obtuse angle. You do inverse cosine of that answer, and there you go. You get 118.6 degrees for C. Okay, then from there on, since you know that one's obtuse, you know the other two angles have to be acute, because we're dealing with triangles here. So if you want to, you can use law of sines to find one of the other ones. You can say, sine of C over C equals sine of B over B, if you want. So you could say sine of 118.6 degrees over 59.3 centimeters equals sine of B over 42.8 centimeters. Alright, go through, solve for B. Let's see here. So sine of 118.6 times 42.8, then divided by 59.3, then do the inverse sine of that. You get 39.3 degrees. And that's for angle B. Alright, and then finally, subtract from 180, the 118.6 plus the 39.3. And you get 22.1 degrees. So now we've been able to go through and find all the angles here. So law of cosines gives us a nice way to do this, and we can easily see if that largest angle is going to be acute or obtuse just based on right here on what the cosine equals. If the cosine equals something positive, you know it's an acute angle. If the cosine equals something negative, you know it's an obtuse angle. And that's exactly what makes law of cosines a really great way to solve those triangles that have that ambiguity to them. Back when you talk about law of sines, you've got these ambiguous triangles where you have to figure out, is it 0 triangles, 1 triangle, 2 triangles, etc. Well, if you've got one of those, like, let's see here, you've got I'm just trying to pick one. Let's say you've got one that's like, I think I did this one in another podcast, but let's say you know that angle this is not to scale as usual, but let's say you know that angle B is 68.7 degrees, and let's say you know that side B is 25.4 inches, and let's say you know side A is 19.6 inches. And you got to go through and solve this triangle. But you can still use law of cosines. Like here, you can use the one, since you know angle B, you can use the one that says B squared equals A squared plus C squared minus 2 times A times C times cosine of B. And you can say, well, I know B is 25.4, so 25.4 squared equals 19.6 squared plus C squared minus 2 times 19.6 times C times cosine of 68.7 degrees. And what you're going to end up with is a quadratic here, because you'll have C squared minus whatever this comes out to, C, plus whatever this is minus this, equals 0. And you can solve that quadratic equation for C. You're going to get two answers, positive, negative. But since we're talking about the length of a side of a triangle, you're going to go with positive. So you'll be able to do that to find C. And then you can, once you know C, you know three sides in an angle, you can then go in if you want to and use law of sines or some other method to find the other two angles. So that is doable. Like with the ambiguous case, no more really, you don't have to use law of sines. You can always use law of cosines, and it'll cut out that issue with figuring out what's going on as far as 1, 2 triangles. It'll fall into place more readily with law of cosines. So that's something to check out. And if you do have two positive answers, then you're like, oh, okay, now I can work with either one of those and see what happens. But if you have a positive and a negative, you can throw out the negative. Or if you had two negatives, you have to throw them both out. So you can look at the way the answers are for the quadratic equation to decide what your situation is really quickly for the triangles there. Alright, then one more thing to wrap up law of cosines. I wanted to show you Heron's formula. Heron's area formula. This can be used for side, side, side triangles to find area. I am not going to go through how this is derived. If you do a search for Heron's area formula derivation, or probably your current textbook has it in it. I know the textbook we're using, at the time of this podcast, it actually goes through and derives the formula in that section where it talks about Heron's formula. Other textbooks I've seen have the derivation in an appendix somewhere. So usually you can find it. It is derived using the law of cosines, and that's why they put it here. It's rather interesting, but it's a little lengthy, and you don't need to memorize how it's derived. I just want to show you what the formula is, and you just need to be able to use it. For this one, you have a triangle ABC, where you know the sides ABC. You don't know anything else. First, there's something called the semi-perimeter. Basically, it's half the perimeter. Remember, to find the perimeter of a triangle, you add up the sides, A, B, and C. Semi-perimeter then cuts that in half. Heron's formula says to find the area, take the square root of the semi-perimeter times the semi-perimeter minus the length of A times the semi-perimeter minus the length of B times the semi-perimeter minus the length of C. Notice that all of that is underneath the square root sign. So let's say, for instance, you have, let's say you have a triangle with sides 262, 599, and 834. So let's say you have 262 miles, 599 miles, and 834 miles. Okay, so you have that. And you want to figure out the area. Well, area normally is 1/2 base times height. In this case, you know the base. The height, though, that's trickier. So what we could do instead is use Heron's formula, knowing all three side lengths, to find the area. Well, first, let's find the semi-perimeter. Half of the 260. I don't know why it keeps doing that. The 262 plus the 599 plus the 834. So that's half of 1695. Let me double check. I just did that in my head. 15, carry the 1, 7, 16, 19, carry the 1, 3, 8, 16. Okay. Then half of that would be 847.5. Alright, so then if we're doing the area, we're going to take that 847.5 times 847.5 minus 262 times 847.5 minus 599 times 847.5 minus 834. All of that's underneath the square root sign. Fun times, eh? Alright, second function, square root. We got 847.5 times 847.5 minus the 262 times 847.5 minus the 599 times 847.5 minus the 834. Look it over real quick here, make sure everything looks in order. Hit enter. And we get about 4,800. I think I read that wrong. 40,800 square miles. Sides were in miles, and this is area, so we say square miles. So I found the area using Heron's formula. Okay, so you need to know the formula and know how to use it for your test. But if you're interested in seeing the derivation, just check out whatever textbook you have currently. All right, well that concludes Law of Cosines. So now you are able to handle oblique triangles, finding lengths and angles, because you now have Law of Sines and Law of Cosines to work with. So now you can handle any of the cases that may be thrown to you. Thank you for joining us, and I look forward to seeing you again soon.